Alrighty, so we are going to start hyperbolas today. We'll finish them Monday, like I already said. And got a lot of new vocabulary, got a lot of old vocabulary. Nice thing about hyperbolas is that they're very similar to ellipses for a lot of the stuff that we name. Their equations are very similar. Focus points are still the C away from vertices, things like that. If you recall, last couple days we talked about ellipses, and I told you that the ellipse is the set of all points that were the sum of the distances from the two focus points. Remember that? And I said if you add up the two distances from the focus points, you're going to get a constant number, and every point on the edge of the ellipse, it adds to that same number, the distances do. Well, a hyperbola, which is two things, they look like parabolas, but they're not. The hyperbola is the set of all points in a plane whose distances from two fixed points in a plane have a constant difference instead of a constant sum. That's literally the only difference between a hyperbola and an ellipse. And if you look at the equations, the only difference is instead of a plus in between the fractions, you have a minus. Thing about subtraction, though, order matters. We'll get to that in just a minute. Those 2 points that we have the fixed distance from, yeah, those are still called focus points. And the line that goes through the foci is still called the focal axis. That's not new. The point that is halfway between the two foci is still called the center. That's not new. It's also halfway between the two vertices, but anyway. And the point where the hyperbola intersects with its focal axis is still called the vertices. So all that is exactly the same as it was for ellipses. And one more similarity between the two is any line segment that has its endpoints on the hyperbola, beginning and ending on the hyperbola, is called a chord. There we go. Now, when we were talking ellipses, we had a major chord on the major axis and a minor chord on the minor axis. They were called major and minor because one was larger than the other. Unfortunately, we can't use that vocabulary anymore. So when you say the chord that connects the vertices, we can't call it the major chord because there's no guarantee that it's actually the longest distance. You see, from top to bottom here is longer than from side to side. So because we can't guarantee it's the longer of the two, what we call it is the transverse axis. The word transverse means to cross. It literally crosses from vertex to vertex through the center. It's called the transverse axis. And perpendicular to the transverse axis is called the conjugate axis. So again, we can't use the terms major and minor anymore because, well, there's no guarantee that the transverse is the longer one. Now, just like with ellipses, half of our major axis mattered, we call it the semi-major axis. Half of our transverse axis matters, we call it the semi-transverse axis. And that will still be A. With the ellipses, half of our minor axis was B. We call it the semi-minor axis. Well, it's still B, but it's now called the semi-conjugate axis. So we have to draw a bunch of stuff on this picture. A lot of vocabulary. You do need to know all of the vocabulary for the tests. Center is still H comma K. That's nice, and I actually have it typed up on this one, unlike the other ones. I would like for you to look at the difference between this equation, which has a left-right set of hyperbola, and this equation, which has a set of up-down hyperbola. What do you think is causing that difference? Yeah, the x's and their y's are switched. Because the order of subtraction matters, the first fraction will always tell you the direction that the hyperbolic curves open towards. So if it's under the x's, if the x's are first, then that is going to open left and right. If the y squareds are first, it's going to open up and down. Now, this box is not actually part of the graph, but we will use the sketch of this box to help us graph these things. The size of the box is determined by A and B. So your center is HK. The distance to your vertex is still A, just like it was for an ellipse. Bless you. So from here to here, is A, our semi-transverse axis. This is B, the semi-conjugate axis. For ellipses, the larger denominator determined direction. For hyperbola, whichever one's first determines direction. The size of the box is determined by which denominator is bigger. So you can see in this sketch, the B denominator, B squared, would have been larger, and that's why this is a tall box. But if A squared had been the larger number, then the box would have been squat and wide. But as long as X squared came first, it still would have opened that direction. Your focal axis is going to go through both foci. For this hyperbola, that focal axis is horizontal. And all horizontal equations have the same basic setup. They are all y equals a number. And since it goes through the center, it has the same y value as the center. And just like with the ellipse, your focus points will be C away from the center. And that's true for the vertical and the horizontal hyperbola. I guess I should go ahead and fill this one out too. That's C. Here's A. And here is B. There we go. But since they are C away from the center, we just have to determine, am I adding them to the, adding and subtracting, excuse me, to the x's or the y's? Well, for this image, it's left and right. That's you changing your x's. So what you would do is, you would figure out what h comma k is, and you would take your h value, your x, you would either add, actually you would add and subtract c. But for the vertical one, obviously, you wouldn't add and subtract c to the x values because that would move you left and right. So for the vertical hyperbola, we're going to add that c value to k. So k plus or minus c. Oh, I forgot to fill in my focal axis for the vertical hyperbola. Focal axis is a vertical line, and all vertical lines have the same basic setup. X equals a number. Again, since the focal axis has to go through the center, it's going to have the same x value as the center. Just like with the ellipse, our vertices are A from the center. So in this image, it's A left and right, which means add and subtract A to the x value of the center. That's the horizontal hyperbola. But for the vertical hyperbola, your vertices are above and below the center, which is you altering the y's, just like we did for the focus points. So h comma k plus or minus a. So the semi-transverse axis, A, semi-conjugate axis, B. And then we have our Pythagorean relation. For the ellipse, the Pythagorean relation was set equal to a squared. The reason why is because in the ellipse, A was the longest distance. So B squared and C squared had to sum to the larger one. But for hyperbola, because the focus point is further from the center than the vertex, the distance from center to focus point will be the longest distance. Therefore, our Pythagorean relation is exactly what we expect a Pythagorean theorem to be. A squared plus B squared equals C squared. Again, because C is larger than A. So it's going to be summed up to C squared. And then what I consider to be the hardest concept to master, not understand, but master, are these slant asymptotes. If you think back to Algebra 1, all you need to find the equation of a line is a point and a slope, and we could use point-slope form. For both images, my asymptotes both go through the center. So this x1, y1 is hk. But let's talk about the slope. Let's do the slope of this line here. If I start from the center and I'm trying to get to here, so start here, trying to get to there using rise over run, I would have to go up, which is b, and go to the right, which is, that's a slope of b over a. Now if I was looking at this line, it would be down b to the right a. So it's plus or minus b over a. And lastly, you would just add this k to the other side, giving us our asymptotes for the horizontal hyperbola to be y equals plus or minus b over a x minus h plus k. You're welcome to try to memorize that, but I don't have it memorized. Just like with the ellipses, I have to draw these things. So I literally draw the box that you see here, and then I ask myself, is this slope a b over a or is it a over b? Because guess what? If you look to this one, the slope is up a, right b, down a, right b. So for the left-right, your slope is plus or minus b over a. But for the up-down, your slope is plus or minus a over b.
What do you plug in for x?
You don't plug in for x for this equation. The x and the y are the variables.
You have two variables and you can't just straight up solve the equation.
There's nothing to solve. It's the equation of a line. When you were graphing lines in Algebra 1, like y equals 2x plus 1, there's nothing to solve, is there? It has two variables.
Yeah, but why don't you just draw the box and draw the line from the box?
You do. I draw the box and then I'll connect the corners. But if I want the equations of the asymptotes, you would have to be able to give it to me.
Are we going to need the
Yes, you need the equations of the asymptotes. There are times where some of the only information I give you is one of the asymptotes. So you would have to be able to dissect it and realize, oh, if I have the asymptote, I know the center, and I know A, and I know B. But which one is A and which one is B is the question. And that's determined by which direction the hyperbola faces. Again, I don't have it memorized. I draw a box with A and B, and then I just decide, is it A over B or is it B over A? You'll see. You got this. I believe in you. Is there anything else I needed to write on this before I start examples? Doesn't appear that way. It looks like I've given you everything we need. Okay. Let's tackle the back of this page, and that's all we're going to do for today. It says find the vertices and the foci, and you know what? Because it's really good practice and you need to be a master of it, we're also going to find the equations of the asymptotes. All right? Before we can do anything, though, this equation is not in standard form. Just like the ellipse, it has to be equal to 1. So we're going to divide by 36. And reduce. That reduces to x squared over 9 minus x squared, y squared over 4 equals 1. My x's came first. That tells me the direction that my hyperbola opened to. So do they open up, down, or do they open left, right? They open left, right. But before I go sketching my left, right, I need to think about the dotted line box. This box. I need to think about that thing. The transverse axis is always determined by the first denominator, because what comes first is always going to be a squared. So if a squared is 9, then I know a is 3. The second denominator is always going to be b squared. If b squared is 4, then b is 2. The box that I'm about to sketch is wider than it is tall. So I have a box that is wider than it is tall, and I have hyperbola that open to the left and right. Picture not drawn to scale. It's just for our brains. Like that. A box that's wider than it is tall. There's my center. I'm going to sketch out my asymptotes. Like Anthony said, we're just connecting the corners. What I do know is that my vertices are to the left and right because x came first. So this hyperbola will look something like this. We also know that our focus points are out here. First thing it asks for is vertices. The vertices are always going to be A away from the center. Then we'll have to find the foci, and the foci are always C away from the center. Well, I don't have C, but I can find it. Where's the center of this hyperbola? Yeah, it's at 0, 0 because there are no parentheses, so it's just 0, 0. So in order to get to my vertices, I have to go left A, which is left 3, and I have to go right A, right 3. That changes my x value. So my vertices are 3 left of 0, 0, which would be negative 3, 0, and 3 right of 0, 0, which would be 3, 0. I can use a squared and b squared to determine c squared. I need c squared because c is how far to the left and right I have to go to get to those guys right there. And because c is larger than a, the Pythagorean relation for this one adds up to c squared. So c squared is 13. Meaning that c is the ugly number square root of 13. I have to go left root 13 and right root 13 of this to get to my focus points. Yes, ma'am?
Is it not c squared plus b squared equals a squared?
Not for the hyperbola, no. That's for the ellipse. And the reason why is because in the ellipse, a is longer than c because your foci are inside the object, where for the hyperbola, your foci are outside of the object, so c is longer than a. So that's how I've always remembered which one goes with which shape, is because I know that c is always how far away my foci are from the center. So if c is shorter than a, because they're in the object, for ellipses, it needs to be b squared plus c squared equals a squared. It's the bigger. But for this one, they're outside the object, c is larger than a, okay, a squared plus b squared gets me c squared. And we said left and right root 13 from here.
Is the reason that a squared plus b squared equals c squared work the same reason the other one works? Because when you shift, that c object creates a red triangle?
Yes. So the thing that I did with the like tie back or whatever the thing is called, yeah. So as if you put the little stick here, as you push this dot up, this dot would be forced to drag to here, and it forms this right triangle. Whereas the hypotenuse now from, and I know I didn't put it on here, but from this dot to this dot is also the length of C. Yeah, because it makes a right triangle in there. Absolutely. Okay, and lastly, I want to find the equations of the asymptotes because I think that that is good practice. We know it's going to be y equals plus or minus, and we know the center is 0, 0, so it's literally just going to be a number with an x next to it. But we need to know, is it a over b or is it b over a? I don't know unless I look at my picture. I could see that a is left and right. That means this slope is rise b over run a. This one's going to be b over a. B and a are right here. And there it is. Pretty neat, huh? X. Yes, I forgot to put an X. Good call. Thank you. Now, what's unfortunate for the video is that it's recording this paper only, and it's not going to be able to see what I'm about to show you guys on my panel. And I don't have a way of fixing that. That's a shame. So I'm just going to pause the video. That way they don't feel like they're missing out. All right, so done nerding out over the image that was on Desmos. Yes?
How did you know the shape of the thingy of like the box?
How did I know the shape of this box?
Yeah.
So we know that it's a left-right hyperbola because x came first. But the length and width of the box are defined by these two numbers. The first denominator is always going to be a squared. So because this was a left-right hyperbola, my a was left-right. So I had to go left 3 and right 3. So I have a box of width 6. And if a squared came first, b squared came second. So my value of b must have been 2. So I have a 2 up and a 2 down from this center, giving me a box that is 4 units tall. Completely coincidental that b squared is 4 and the box is 4. It's just because 2 squared is the same as 2 plus 2. But that's how we knew. Okay? All right, good question. Let's tackle this last one, and we will call it a day for today, and it'll be an easy Friday. I'm going to talk about what we're going to do Monday, but here we go. We have foci at 0, -3 and 0, 3. I'm going to put little f's on them so I do not think that they are my vertices. The fact that my foci are up and down from each other tells me which letter comes first in the equation. Y is going to have to come before x. So I'm going to have a y squared fraction before an x squared fraction. Also, halfway between my two foci, what will I always find? The center. You were close. Here's what we know then. Not only do we know our center is at 0, 0, so in our fractions, there won't be sets of parentheses. They'll just be x squared and y squared. And actually, y squared will come first. We also know what c equals. Because this distance is c. We know c is 3. So we know that c squared is 9. And we're going to need that knowledge. What else do we know? We also know that the conjugate axis, which is perpendicular to the transverse axis, and this is the transverse axis because it literally crosses from focus to focus, our conjugate axis has a length of 4. So what is our semi-conjugate axis? 2. And what letter is our semi-conjugate axis? B. So we know that B is 2. That means to the right 2 and to the left 2. I'm putting red dots there because I'm going to use that knowledge to draw my box. The last thing I need is a squared to figure out how tall my box is, aka where my vertices are. Well, I have b squared and c squared. The Pythagorean relation for hyperbola, since c is the longest length, is a squared plus b squared equals c squared. A squared is an unknown, b squared is 4, c squared is 9. So a squared for us is 5. That's enough information to write the equation. But I want the equation, I want the asymptotes, and I want the graph. I want it all. I know what the directions say. I want more. And I know that the top and bottom of my box, where my vertices are, will be determined by a. A is the square root of 5. Now look, I don't know what the square root of 5 is, but I do know that it is bigger than 2, but not much bigger than 2, because 2 times 2 is 4. So I'm going to put my vertices here-ish and here-ish. And then I'm just going to sketch out my box. This gives me the ability to sketch out my asymptotes. So our hyperbola looks like this. Let's get the equation. We already know that y squared comes first because it's an up-down hyperbola. The first denominator is always a squared. The second denominator is always b squared. There's the equation of this hyperbola. Lastly, the asymptotes, and I would say that we have found everything we need to know about this hyperbola. Y equals, and since the center goes through 0, 0, we know that my hyperbolas are going to be plus or minus a number x. Not my hyperbolas, the asymptotes for my hyperbola. So plus or minus some fraction of x. We just need to figure out what the fraction is. And now that I have a picture, I can come here and I can say, is my rise a or is it b? No guessing aloud. Remember, from center to vertex is always a. That's true for ellipses and for hyperbolas. So in this box, my rise is a. My run is b. So a over b. My a value was root 5. And my b value was 2. And there it is. That's all we're going to do for today. Any questions on that? Yes?
Why is the denominator 5 under 1 squared?
Why is this denominator 5?
Yeah.
Because the denominator of the first fraction is always a squared.
Oh, okay.
A and b are the square roots of those denominators, but the first one's always a squared. Okay? Any other questions on it before I stop the video? No? All right.